take a little step back. So we're all interested in this because we're all observing things that are going on, events in the climate system. We saw the first 40 degrees C plus temperature in the UK a couple of years ago. We've had this catastrophic flooding in Germany and the lowland countries a few years ago. Last year in Spain, in Valencia. We've seen droughts. This is actually Bodmin Moor in the UK. It does sometimes have droughts. But wildfires as well is another thing. You know, there's a human aspect to these. There's also a weather aspect. The Santa Ana winds were strong, but there's also a climate change aspect. The atmosphere is more thirsty, it's more capable of drying the soils more rapidly. All these things are going on, but how much of this is weather, how much of this is human, how much of this is due to climate change? So we can look back in time, and we'll do this later on in the course, but we know that climate has always been changing. The configuration of the continents have changed over many hundreds of millions of years, and that produces almost a different planet in terms of climate, how much ice can be stored on the poles or not at all, how the ocean circulates, like we mentioned earlier on. So over many hundreds of millions of years. We also know about the fact that the Earth's orbit around the Sun, it's not a constant, it's not a circle, it's an ellipse. That ellipse becomes more and less elliptical. The axis of the Earth's rotation, which gives us the day and night, that's tilted with respect to its movement around the Sun. That gives us the seasons. So we're tilted, northern hemisphere is tilted away from the Sun at the moment, the summer is tilted towards. But the degree of that tilt varies over tens of thousands of years. So it makes seasons stronger or less strong. How elliptical the orbit is changes over many tens of thousands of years. There's a 100,000 year and a 400,000 year cycle. That can alter the distribution of sunlight over the planet. And we know from these kind of things, so sometimes called Kroll-Milankovitch cycles, that there's been these well-known periodic changes in how the Earth orbits around the Sun, and these have introduced these glacial cycles. So if you went back 20,000 years ago, we were in the last glacial maximum. The configuration of the orbit around the Sun was such that you had extra heating at certain times of year in certain regions, and that meant that there was a melting of ice that initiated a massive feedback. You're massively reducing your amount of ice, and that helped to send us out of the last glacial maximum into our current interglacial. But there are other feedbacks that went along. We've talked so far about carbon dioxide being a forcing because we're just suddenly adding CO2 to the atmosphere, but over glacial cycles, we've actually had changes in carbon dioxide, which are natural. So if you drill down 2 kilometres into Antarctica, which they did, it's like a million-year time machine, essentially. The further down you go, the further back in time you go, you can get back at least 800,000 years. And in the water molecules, you've got isotopes. So isotopes are, with hydrogen and oxygen, the same chemical effects, but you can have different numbers of neutrons in the nucleus to make them heavier or lighter. So you can have heavy water, light water, and heavy oxygen, lighter oxygen. And the ratio of these can tell you about past climate change. It can tell you about the equator to pole difference in temperature, but it can also tell you how much water is stored as ice in the poles. And we can also tell from other things, that going back to the last glacial maximum, sea levels were 120 metres lower because all that water was stored as ice in the northern continents, giant ice sheets. But the other thing you can look back, so you can look at temperature changes and they respond over glacial cycles. So it's maybe 5 or 6 degrees C colder globally at the last glacial maximum than it was in now. But you can also, in these ice cores, you can see tiny trapped bubbles of air. So it's like fossilised evidence of what the atmosphere was. So you can go back nearly 800,000 years ago. And this shows you carbon dioxide varying also. So in a colder climate, the CO2 is more able to dissolve in the ocean, so you draw down more CO2. In a warmer climate, it outgasses more CO2. There are other effects over land. This means that as we came out of the last glacial maximum, we suddenly had an outgassing of CO2 that raised CO2 levels from about 180 parts per million up to 280 parts per million. And that is actually a feedback because it's responding to the warming and it's amplifying it because you're warming coming out of glacial period because of the orbital factors, and that's being amplified by these ice sheet effects, and it's being amplified by the greenhouse gas effects. So it makes the warming larger than it would have otherwise been when we shot out of the glacial period. And it's interesting to know that anatomically modern humans have only been around for this period here. We've only lived through a couple of interglacials. But what is the does anyone know what the CO2 level is today?
380.
Yeah, so it was 380 not long ago, so now it's 420. Yeah, so that's where it is now. So actually, as of more than lower, as of the other last week, the last annual average was 424.8 parts per million. So even you were slightly outdated. So you can already see that, okay, this is not natural, this is so far out of natural variability of CO2. And this is because we've burnt, most of the forests that have ever existed, these huge forests that went down in Carboniferous period when there was a certain type of wood that didn't really break down and stored all this amazing amounts of coal, oil, natural gas. And we've suddenly, from the carbon cycle, moved all this carbon straight back out into the atmosphere. And that's what's driving the warming today. So looking at the what the carbon cycle is at the moment, so this just shows you a lovely picture of fluxes of carbon. And they're in gigatons of carbon per year, so billions of tons of carbon. So sometimes you'll see things in gigatons of carbon, sometimes gigatons of carbon dioxide. So remember, CO2 is much heavier than carbon, so you have to make the adjustment for the molecular masses of what carbon and oxygen are. So be careful with that if you ever do that in your future career. You can also see gigatons of carbon dioxide equivalent, which is then adding in other greenhouse gases, the warming effect that would be equivalent to their same increase in CO2. So that's the other thing, but that's an aside note. This is just gigatons of carbon, most of this is CO2. What we see is natural fluxes in blue, so we get massive fluxes of carbon dioxide from the land into the atmosphere and back again, from the ocean into the atmosphere and back again. These are the anthropogenic, human-caused carbon fluxes. They're tiny, they're pitiful. I mean, they're tiny compared to these ones. But the key thing about the natural ones, of course, is that they're in balance. What comes out goes back in during the course of the year. As you're growing all that vegetation in the northern hemisphere spring, you're drawing down carbon to make the stems of plants and things like that. And as they degrade later in the year, that kind of comes back out again. So you're in a balance. These fluxes are not in balance, you're perturbing the balance. So we've got about 10 gigatons of carbon per year coming out as burning fossil fuels, a little bit from cement making as well. And through land use change, chopping down trees and things like that, we've got another 1.6 gigatons of carbon per year. So about 11 gigatons of carbon per year going into the atmosphere. And you could probably calculate what the CO2 change should be per year based on that, knowing what these values. But actually we're lucky because we're sending more CO2 into the atmosphere, the carbon cycle is being put out of balance, and actually that's causing more growth of vegetation on land, more drawdown in other ways of carbon into land, and more drawdown, the balance between atmosphere and ocean in terms of the CO2 is out of balance, so that's drawing down extra CO2. So luckily for us, only half of what we emit is left in the atmosphere. But that 5 gigatons of carbon per year is increasing CO2 in the atmosphere by maybe 3 parts per million every year, year on year. So CO2 concentrations, as we've seen from the ice cores, we know that they're well outside of that natural variability in the last 800,000 years, and based on other evidence, definitely highest for the last 2 million years, possibly as much as 10 or 20 million years. So we've tipped things out of balance, we're raising the CO2 in the atmosphere, and that's causing the warming of the planet. Yeah, and this one we have, of course, can't not show the climate stripes. So Ed Hawkins' climate stripes showing this warming as a series of blues as cold and reds as warm. Plot this as a graph. We have the fact that we've warmed things, so going from this is relative to 1961 to 2010 climatology, relative to minus 0.6 in the pre-industrial period. Here we've gone up to, as of last year, Ed had to come up with a new colour because things were getting so warm. We've got up to maybe 0.9 degrees C above the 61 to 2010 climatology. So 0.9 plus 0.6 is rather worryingly 1.5. So in that year we reached 1.5 degrees C above pre-industrial, which, as the observant of you will know, is one of the Paris Climate Agreement goals, where we should strive to keep the temperatures below 2 degrees, limit it to 2 degrees above pre-industrial, and if possible below 1.5 degrees. So that's the first of the Paris climate goals. Now the Paris Climate Agreement, I did have a look at it. It doesn't actually say that a single year shouldn't count, but actually all climate science people know and policy people know you've got to average things over maybe 20, 30 years or so. So it's generally assumed you've got to have a 20-year at least period that's 1.5 degrees C above pre-industrial. That's what's associated with the impacts that we're trying to avoid, essentially. So we've got this massive warming, and we know, based on the observed warming is driven by the emissions from human activities. So we've seen earlier on with those radiative forcing plots, we've seen that greenhouse gases have been warming the planet. The aerosol cooling has offset this to some extent. We also know that the warming is amplified by feedback loops. So you've got the water vapour, you've got ice, and cloud probably is also an amplifying feedback loop. And these make the warming, you need to increase the temperature more to get back to equilibrium, so it's making the warming larger than it otherwise would be. And when you do actually complex models, you can do this in a simple model, and you'll get the chance to do that next week. You can run laboratory cases, essentially, of saying, well, if we run with the observed radiative forcings, what temperature change do we get? And we can have, we can do the case where we just run with natural forcings, so changes in the solar cycle and longer-term changes, and volcanic clusters of volcanoes, etc. And you can see the volcanoes coming through, but mostly you're not really getting any warming at all, depending on a bit of cooling at times. Whereas if you run simulations with the observed warming, you can more or less get the observed warming, but there's this big uncertainty range, and that uncertainty range not only relates to this uncertainty in the feedback loops, it relates as well to uncertainty in the radiative forcing. So we'll do that a bit more next week in this assessment. But you can generally say that the greenhouse gas increases offset slightly by the aerosol cooling has driven this warming. And you can look back over a longer period based on, for example, tree rings and other geochemical evidence going back over the last 2,000 years. You can see a general decline which relates to the orbital configuration changing. The optimum period for warming further back, and it's been declining slightly, and then you get this rapid warming at the end. And you can see that the level of the warmth that we've reached now, the rate of warming is the largest in the last 2,000 years, the last 50-year period. But the actual warmth of this decade, it's the warmest part in this interglacial. It's probably equal and probably a bit larger than the climate optimum periods, some periods that we've seen. But the last time that the planet was warmer, based on the evidence we have, was the last interglacial period, which was 125,000 years ago. And that was when sea levels were, so in the IPCC it was 5 to 10 metres higher than today. There was a recent paper that's come out saying actually it probably wasn't that high. But these things are uncertain. But anyway, that was the last time things were warmer. It's a shorter but sharper interglacial than one 125,000 years ago. And what we do know about, I'm not going to go in too much more detail, but you're going to go on to this later on in the course in terms of what this means, what are the projections of climate change, how will this alter very soon. So in terms of the water cycle, some of the biggest impacts are going to be seen in the water cycle. We've already seen big flooding events, we've seen droughts, we've seen wildfires. How much of this is related to climate change? But we do know that as the warming continues, that the global water cycle will intensify. And that goes back almost to the simplification of the Clausius-Clapeyron equation. We know that a warmer atmosphere is a more thirsty atmosphere. It wants more water. It's almost more effective at sapping water from the source region, so it's more effective at getting water from the ocean, but it's also more effective at sapping moisture from the ground, so you have more rapidly onsetting drought conditions, for example. And the winds then transport this extra water vapour in the air that's also amplifying climate change through a feedback. It's moving that water from the source regions into the sink regions, the storms, the mid-latitude weather systems, the tropical convection, the monsoonal belt. And when there's more water in an atmosphere, you're converging this water into these systems and producing a greater intensity of rainfall. So we know that there's going to be more intense rain when you do get heavy rain in the warmer atmosphere because of these simple thermodynamic factors. But on the other hand, we're going to onset droughts more rapidly because the atmosphere is more thirsty for water in other regions. And what this also means is not only that wet regions and dry regions can do different things, but even the same region can do different things on different times. So one year we might have very wet, much wetter than normal conditions because of the extra water vapour in the atmosphere. Other years it might have more rapidly onsetting and more severe drought conditions. So that shows you can get more variation, more fluctuations. It's actually been called recently in the literature a climate whiplash. You get more strong fluctuations between wet and dry in one region, and you get more contrast between wet and dry in different regions as you get these extreme events going up over the globe. Going back to the wildfire thing as well, you do get the issue of you can get situations where you can get more rapidly growing vegetation in one season, more rainfall in one season, but also higher CO2 levels, meaning there's more rapid growth in vegetation. And in other seasons, you have more rapidly onsetting and severe droughts. These two can go hand in hand in making wildfires worse. So while wildfires are caused by people in a lot of cases, as well as lightning, but they're also caused by weather conditions. Climate change can make wildfires worse, as well as making extreme rainfall and associated flooding worse, as well as making extreme severe droughts more severe. So there's a lot to unpack from that, and that's kind of covered in one of the IPCC chapters. So looking further forward, we can make projections. So we showed the case where you could use climate simulations, and Phil Collins will talk more about how we construct proper complex climate simulations rather than our Excel spreadsheets or Python ones. Rather than just doing a laboratory experiment where we try and understand the past of climate change, you can also project out into the future by saying, well, what happens if we go on this pathway of socio-economic change or this pathway? What will that mean for emissions? What will that mean for radiative forcing? And you can plug these into the climate models, and then the models will produce their own emergent feedbacks on their own. You don't prescribe them, they just happen. And the climate will shift, circulation patterns will move, and you'll get changes in temperature. So this just shows a typical one from the summary for policymakers from the IPCC report, looking at the historical period from 1950 to present, and then the future projections on a different bunch of scenarios. So some with very low greenhouse gas emission scenarios, some with very high and possibly implausible greenhouse gas emission scenarios. And it shows that the only way we can limit climate change to 1.5 degrees C is through this very, very low scenario. We've probably missed the boat on that one. But you could be expecting in the highest emission scenario a warming of nearly 5 degrees C relative to pre-industrial by 2100. And again, just to put that in context, the last glacial maximum, that was when the world was maybe 5, possibly 6 degrees C colder, and that was a very different planet we were on then, with ice sheets moving across the northern continent. So this is a fundamental change in our planet. even, that's why the IPCC have even shown that anything above 2 degrees C is probably, you really don't want to consider that. But at the moment we're kind of heading for maybe 3 degrees C based on current policies that might not carry on based on recent political developments. So the other thing you can look at are other aspects, so ecosystems, so Arctic sea ice area, we've seen a decline. It's been actually quite flat for the last 10 years, Arctic sea ice, but the old ice has still been melting. So the 5-year-old ice has dwindled to almost nothing. And you're getting this more transient seasonal ice forming quickly in the autumn and then melting again. So we're seeing a decline, and again, the only way you can save this Arctic ice is going in these 2 low emission scenarios. You're going practically ice-free is considered below 1 million square kilometres, and you're going to go through that line by 2050 with some suggestions it could be earlier than that. And then the other aspect of climate change that relates to kind of what we talked about today in terms of transient climate change and the fact that how the ocean takes up heat. As the ocean takes up heat, it expands and that raises sea level. But also, as you mentioned, melting of ice, that adds water to the ocean and that is also raising sea levels. We've already seen a rise in sea levels of maybe 20 centimetres or so. And then these are projections out to the future. And sea level rise is a very long-term problem because, as we mentioned with the ocean, it doesn't really like to circulate much, it does it very slowly. So the amount of time it takes for the deep oceans to really heat up is, it takes hundreds of years. Even though you've pretty much reached your equilibrium temperature, the deep oceans are still taking up some of this heat and still expanding. And the ice sheets will also take a long time to get to their new, smaller equilibrium masses, and that will continue to pile water into the ocean. So we've got possibilities of between half a metre and 1 metre of sea level rise by 2100, based on these projections. But in the IPCC report this time, we also wanted to look at the low likelihood but high impact scenarios. The reason for doing this is why we insure our house. We're insuring it against these low likelihood, high impact events that we would never be able to afford. In a risk framework, that's still important because risk is the magnitude of the hazard times its probability, essentially. There's also a vulnerability aspect in there as well. So there's a possibility that ice might melt more rapidly because, for example, one method is that you're lubricating the under part of ice sheets as you're melting them, and this could make them melt more quickly. That's one idea. There's other possibilities of algal growth on ice, making them darker in a warmer world, and that encouraging the melt. So we've got the possibility even of getting way out to well above 1 metre. And not to want to give you nightmares or anything, but if we're looking at 2300, even in the very lowest warming scenario, we've got a sea level rise of up to 3 metres. Because the oceans are continuing to take this heat up, the ice sheets are continuing to shrink. And in the very high greenhouse gas emission scenario, anything above 2 metres up to even maybe 10 metres. And there's some paleo evidence that goes into this as well. But that's obviously, personally, we don't need to worry about this, but these are huge magnitudes, planetary changing sea level rise that we're going to see over the next few hundred years. Which then brings you to, okay, well, what do we need to do about it? And we will kind of know, apart from certain politicians, but there's this very simple relationship between CO2 emissions. In this case, we are gigatons of CO2. I can't remember if it's CO2 equivalent or just CO2, it might be CO2. So these are cumulative emissions of carbon dioxide. And when you plot this against the global temperatures, you get quite a linear relationship. This is a historical period, quite a linear relationship. So as you're continuing to increase your cumulative emissions of carbon dioxide, you're raising the temperature by this certain rate. So 1 degree C per 2,000 gigatons of carbon dioxide emitted. We're currently up at this point, and what you can do is just carry on these projections. So this is a very low greenhouse gas emissions scenario with a bit of uncertainty. That's the high one. So you can see this one stops because in the previous one you can remember that it kind of stopped around 1.5 degrees C. So that's the one that's consistent with this one, limiting climate change to 1.5 degrees C. So you can already see that at that point, you can only emit 3,000 gigatons of carbon dioxide into the atmosphere to keep climate change to within 1.5 degrees C by pre-industrial. So that's a very simple then carbon budget that we've got left from that arrow there to where we've got to get to. That's the amount of carbon dioxide left that we have left that we can emit and still keep to this 1.5 degrees C. And there's uncertainty related to this, so there's like probabilities of that. And essentially, as you'll come into next in the rest of the talk, the way to deal with this, of course, is to massively, but not only massively, rapidly cut greenhouse gas emissions. Because in terms of cumulative emissions, if you kind of hold off, it's the area under the curve essentially of what if you're doing rapidly, the area under that curve is quite small. So that's one scenario. That's your cumulative emissions of rapid cuts early, and this is where you get to net zero. This is the other method of getting to net zero, is doing that, panicking at the end, but then you've got this extra area, so you're emitting much more CO2 by getting to net zero in that way. So that's why it's got to be both rapid, it's got to be massive, and it's got to be across all sectors, and it's got to be in a way that's considering societies, considering sensitivities. And the other thing is the difficulty in, for example, the negotiations, and why they're so difficult is the fact that it's an equity problem as well, because a lot of the richer nations are rich because they've emitted so much carbon dioxide, they've used this for their economic gain, so they're the source of the problem, whereas a lot of the poorer countries that haven't done this have less GDP, but they're suffering, they're more vulnerable to climate change, and they're in natural regions that are more vulnerable, and they're going to suffer more of the consequences. So there's got to be a movement in two ways, from rich to poorer, and one of those ways is in terms of the climate finance. That's in moving capital from the causes of the problem to the recipients of the impacts in a way to transition economies to sustainable low carbon economies. That's climate finance, which is part of the negotiations at the COP meetings that you've probably heard of in the news. The other thing is this, how do we help nations that are bearing the brunt of impacts from climate change, that's sometimes called loss and damage, so the movement of funds to account for the fact that some nations have caused the problem and other nations have suffered the problem. You need a movement of capital. And obviously, richer nations want to move a small amount, and nations that are going to suffer the consequences want a larger amount, and you've got to meet in the middle somewhere. There's no right answer, so that's why climate negotiations are difficult. But, on the other hand, they're necessary. So it's got to be a jointly kind of acted situation of taking into account local factors, taking into account nature-based aspects. So you're not only just thinking about climate, you're thinking about biodiversity and other things like that. And it's got to be about linking up different sectors. So it's not just about governments, it's about University of Reading is doing a lot in terms of meeting its net zero, for example. But companies, local councils, but also local communities, all of these have a role to play, including personal and talking about climate change as well. So these are the kind of solutions, and we go on to look a bit more about impacts and adaptation, but also in terms of mitigation. And the other thing to think about that we mentioned earlier is we're probably not going to be able to get to net zero without taking in some extra CO2 from the atmosphere. And the reason for that is there's some things in our society we do need residual emissions of carbon dioxide. So we're always going to emit some, it's always going to be more than the natural. So we need some way of uptaking carbon. So one way is potentially more trees, but that's a very difficult one because it's got to be a permanent change. It's got to be growing trees that are actually going to stay alive and not die a few years later. So that's one small aspect. There might have to be other situations where you're literally, one method, for example, you're putting dust on agricultural land, and that in the weathering process that takes up carbon dioxide. There's a paper in Nature out the other day. They found a new method of making that work much better. So there are possibilities. And the other aspect that's talked about is this geoengineering thing. Can we send something into the atmosphere that maybe offsets some of this warming? So can we seed clouds to make them brighter? Can we do other things, paint roofs white and things like that? So there are other things that we can do. But these geoengineering ideas have difficulties, because if you were to, say, make the planet more bright, you're balancing the energy budget, but you're doing it in a very different way than you're doing it in the sunlight. That's changing heat in different regions than you would be by reducing carbon dioxide. That has massive ramifications to how the water cycle changes, where the monsoon belts are, things like that, so you can have big shifts in atmospheric circulation patterns. So a lot of difficulty there. So I'll finish up then, just to say, we know Earth's climate has always changed, but we know that the changes now are human-driven, based on carbon cycle and other things. We know that the changes are completely out of the natural changes we've seen. We've seen widespread, rapid and unprecedented in thousands of years. We know that climate change will make extreme weather more severe, and we know that the long-term changes will raise sea level rise and have other possible tipping points like AMOC, ocean circulation shutting down, possible tipping points in ecosystems like the Amazon rainforest. So every bit of warming avoided matters. That's another key thing. And limiting warming below 2 degrees requires immediate, rapid and large-scale reductions in greenhouse gas emissions. So I'll finish there.